Hello students, let us continue. The next point is the characteristics of DC shunt generator. To determine the internal external load characteristics of a DC shunt generator, the machine is allowed to build up its voltage before applying any external load. As we discussed last time, the three characteristic curves, the OCC is the same for every machine, so we need it's not necessary to discuss for the shunt. It's the same. So the only thing we have to discuss is the internal and external load characteristics. Once we know either internal or external, we can get one from the other, like what we discussed last time. So to get these characteristics of the generator, we have to make the generator to build up its normal voltage without any connection. First, so to build up the voltage of shunt generator, the generator is driven at a rated speed by a prime mover. We have to apply the rated speed. Then the generator, we have to allow the generator to build its normal voltage at a rated speed. Then, once the generator build its necessary voltage and come to this rated speed without load, we start connecting the resistor. Gradually, we have to load the generator like what you have seen it here. This is a shunt generator. So already the generator is running at a rated speed and it is already start producing the voltage, internal voltage. We gradually load variable resistor and take the reading. What reading are we going to take? The voltage and the current. Connect the voltmeter in parallel, ammeter in series, then try to take the reading and plot IL versus VT. IL versus VT. Then that will tell you the characteristic. So the terminal characteristics of a shunt DC generator differ from that of a separately excited DC generator because the amount of field current in the machine depends on the terminal voltage. Now, in this case, terminal voltage is the one which is affecting IF, this IF. But in a case of separately excited, since they are separated, there is no connection in between. Now, in this case, it is going to be controlled by the terminal voltage. That is their difference. Now we connected the load. What will happen? What will happen if the load on the generator increase? If we increase the load on the generator, obviously IL will increase. IL increased means from the equations in a shunt generator we say IA is going to be IL plus IF, right? That is what the question is saying. IF plus IF. So if load increase in our generator, if the load increased, it increases IL. IL increased means obviously armature current will increase because it is a summation of IL plus IF. If IF increased means from the equation EG minus IARA. So now this increased means obviously VT will come down, right? VT will come. It will decrease the terminal voltage. So this precisely is the same behavior as the separately excited generators. However, what makes it different in this shunt is when VT further increase. Now the difference is here. VT increase means in a shunt generator we said IF is going to be VT by RF. Now VT decreased means IF get decreased. If IF get decreased, obviously flux inside the machine will get decreased. Flux inside the machine get decreased means EG will get decreased. EG get decreased means again it leads to VT further decrement. further decrement. Therefore, the resulting terminal or the resulting terminal characteristic curve will be much steeper than the sorry friend, steeper than the separately isolated DC generator, because both effects, it means increasing of the lower, it decreases VT, decrement of VT, it lead to decrement of the flux inside the machine, decrement of flux lead to decrement of EA, decrement of EA again lead to further decrement of VT further. So VT will drastically reduce it. So if you see this curve, if you remember, it is open characteristic curve. This is if we reduce from open characteristics some flux weakening effect, armature effect, we say we'll get internal characteristics, and if we decrease the field weakening effect from the internal characteristics, we'll get the external characteristics of the curve. So what makes it different from separately excited? The slope of separately excited DC generator is higher than this shunt, and for the shunt it is very steeper, drastically it will reduce. Where in another reference we may get such typos. It drastically reduce because the two effects, the increment of this drop at the same time, the decrement of this EA or EG, both they lead to VT. That's why it is drastically reducing. It is drastically reducing. So the voltage drop is steeper than just the II drop in the separately excited generator. That is, the voltage regulation of this generator is worse than the separately excited generator because it drastically reduces or decreases when compared with a separately excited generator. This is another approach of what I have said before. You can go through that. So we usually apply such type of generator, such type of application where steeper curve is required. We'll see where that it is. And the next point is voltage control of shunt DC generator. After all, our machine is a generator, so it is expected to produce the voltage or power. So we need to control the terminal voltage. We need to control the terminal voltage. So almost the way we control the voltage, the terminal voltage, is similar to a separately excited system. Two methods are there: speed control of the generator and field resistance of the generator. And like we said, in a separately excited, the speed of the prime mover of the generator is more or less, it is limited. There is no such flexibility in the speed of the prime mover. So principally or mainly we use this field resistance control method. As we know from the equation, when we affect the RF or the field resistance, obviously will affect the IF VT over RF. So when we affect this, definitely we will affect this. Means IF affected means flux inside the machine will get affected. Flux affected means internal generated voltage get affected. If internal generated voltage affected, obviously VT will be affected. They are all interconnected. Therefore, we can control mostly the terminal voltage of our shunt generator by inserting the field resistance, variable field resistance on the field winding of the machine. We can control the terminal output of our generator. And the next point is the application. So the application of shunt generator are very much restricted for its dropping voltage characteristics, like we have seen previously, because the curve is drastically dropping. So they are used to supply power to the apparatus situated very close to its position. It means it cannot go longer distance. It cannot go longer distance because IRA will get increased, so drastically drop the curve. So close position supply can be used by using this shunt on DC generator. And this type of this generator generally give constant terminal voltage for smaller distance operation with the help of field regulation from no load to full load. It is very good in supplying constant voltage if it is properly controlled. To do this, this shunt DC generator, they can be applied to general lighting purpose for closer positions. They are used to charge batteries because they can be made to give constant output voltage for charging purpose. We can apply or use such type of generator for giving excitation to an alternator. They can be used as an exciter. It means they give external DC sources for the alternator, and they may be used for small power supplies in a very short distance. This is most applicable area of our DC generator. And next is, let us come to the example on shunt DC generator. This example, for example 1, it says a DC shunt generator delivers a power of 50 kilowatt at 250 voltage. Its armature has a 4-pole wave winding with a resistance of 0.01 ohm, and its field winding is 125 ohm. If the number of turns in the armature is 201 and the flux per pole is 0.02 wave, determine voltage and the speed of the operation. In RPM, it says. Now, as usual, what are the givens? We have to know the givens. The given ones, power is given 50 kilowatt, output power is given. And second, what is given? Voltage of the terminal is given. VT how much? 250 volt is given. And armature resistance is given 0.01 ohm. And field resistance is given RF 125 ohm. See, it is high resistance value. And conductor on total conductance of our armature is given, conductors 201, and the flux per pole is given 0.02. Says so. You should remember those important equations. What are those important equations? In shunt generator, IF is going to be IL plus IF. This is IA, sorry. IA. Armature. And we have to remember this VT EG minus IA RA. So, sorry friend, and what is required? Generated voltage, EG. What is this generated voltage? It is EG is going to be, from this equation, VT plus IA RA. We know RA, but we don't know IA, but we know VT. So what is IA? It is the summation of IL plus IF. What is IF? So we need to get this IL and the IF separately. So we know the IF is going to be VT by RF. Our VT is 250 divided by our RF is 125. So this is going to be around 2 ampere. And what is IL? Load current. What is given? Output power is given and we know the terminal voltage. Therefore, IL can be found from P by V terminal. My power is 15 kilowatt and the voltage is 250 volt. Therefore, IL is going to be around 200 ampere. 200 ampere. Then, what is IA? It is a summation of those two. 2 plus 200, 200, 2 amp. This is the summation. Now, we can directly get EG. EG, it is going to be VT. VT is how much? It is given 250 plus IA is how much? 202 times RA, how much? Is already given 0.01. So our EG becomes around 252.02 voltage. This is a generated voltage. This is a generated voltage. Voltage generated. What we said, A. And what is the next question? B. Speed of operation in RPM. What should be the speed? And what the speed this machine is rotating. So now, from how we can get the speed? From the equation again, EG in RPM we are asked, so okay, find N. This means ZP 16A phi N. Therefore, the speed N is going to be EG times 16A divided by ZP 5. That is N. From this we can generate. Therefore, we know EG. How much it was? 252.02 times 16 times. What about A? Pass, number of passes in the machine. We told that on the equation, the machine is wave winding here. If it is a wave winding, A is always 2, we said. In a lap, A is equal to, in a lap or lap winding, A is equal to P, number of poles. But in a wave, A is always 2. Therefore, it is going to be 2 divided by, Z is already given, 201 times, pole is already given, 4 pole, then phi is given per pole, 0.2. So, if we calculate this, the speed of this generator is going to be 0.74 RPM, revolution per minute. This is a way we have to calculate the speed of operation of the generator. And let us come to the second example. It's almost more or less the same. On the second example, an 8-pole DC shunt generator with 778 wave connected armature conductors and running at 500 RPM, supply a load of 12.5 ohm resistor at a terminal voltage of 50 volt. The armature resistance is 0.24 ohm and the field resistance is 250 ohm. Find armature current, induced EMF, and flux per pole. It's almost similar with the previous one. So, what are the givens? Pole is given 8, pole is given, and conductor is given 778, number of conductor per armature, and speed is given 500 RPM, and load is given, R load of the generator 12.5 ohm, and terminal voltage is given how much? 50 volt, and RF is also given how much? 250 ohm. So what is requested? Is asking IA, armature current, and generated voltage EG, and flux per pole is requested. So similar with the previously, we'll attempt important equations. IA, it is going to be IF plus IL, we say IF plus IL. So what we know, what is IF? It is VT by RF. What is VT? 50 volt. And RF how much? 200, 250 ohm. So IF will be how much? 0.2 amp. Similarly, IL, load. Load current, we know the load resistance, we know the terminal voltage, so we can get from these two. So V terminal divided by RL simply. V terminal is 50 volt again, RL is 12.5 ohm. Therefore, IL is going to be 4 amp. Now, what is IA? Summation of the two, right? So 4 amp plus 0.2 amp is going to be 4 sorry 4.2 amps. 4.2 amp. That is IA. First equation get done. And second, EG. EG, generated voltage, VT plus IA RA. Right? This is the way we can get EG. We know VT 50 plus, right? It's already given. IA is 4.2 times RA. How much? RA is not given, it's given already. RA how much? RA was given to be 0.24 ohm. So it is 0.24. Therefore, just get this when it gives you 51 point. Okay. This is given 51.008 volt, almost 51 voltage is get generated inside the machine. Inside the machine is 51 voltage. So approximately around 51 volts is generated inside the machine. This is the second equation. I mean the second requested point. And as I said, what is requested? Flux. Again from our EG, we can say ZP 16A 5 by N. This is K prime, as you know. This one is K prime. Therefore, it is requested that 5 EG time 16A divided by ZPN. Now, EG we found it is almost 51 times 60 times A we told that it is a wave winding again. So if it is a wave winding, it's going to be 2. It's going to be 2 divided by Z how much? 778 times N given 500 times P how much the number of pole? 8 given. So the flux will be 1.967 milliwave. That is the sorry, wait. That is a flux per pole. That is a flux per pole in our generator. So, sorry. That is a way how we should tackle examples or equation related to the shunt generator. So I highly encourage you to do more and more examples from the references given, and just don't forget those important equations what we addressed in a shunt generator. Lastly, let me write those very important equations for the connection of the shunt generator. So just to remind you, IA armature current, it is IF plus IL, and V terminal voltage, it is ET minus IA RA, and IF is going to be VT by RF. These are very, very important equations what we have to have in our mind always when you think of shunt DC generators. Of course, one can drive just by simply observing the circuit connection of the shunt generator. It's a matter of writing KCL and KVL. This is simply Ohm's law, normal. So, by observing the circuit diagram, we can produce these equations, which help us to analyze the equations related to these shunt generators. That is what I have for today, friends. If you have any questions, suggestions, as usual, you're welcome. Thank you very much to listen.